back to my channel, and today I'm going to be talking about limits. So let's begin by talking about the definition of a limit and then progress forward. So what is a limit itself? A limit is essentially trying to find what f of x is equal to when x approaches a specific quantity, infinity or negative infinity. Let's write this in mathematical notation to essentially get a better essence of what limits actually are. So this is the mathematical notation for a limit. It's a limit as x approaches k of f of x. Now at first this may seem complicated, but we can essentially make this similar by transforming it into a more algebraic sense. Let's make one key substitution. We're going to say that y is equal to f of x. Now plugging that in, we get the limit as x approaches k of y. And the reason for doing so is because when we see the limit as this representation, we essentially can get a better essence of what the limit actually is. So let's consider an example. Let's consider y is equal to 2x plus 3. Now this is a linear equation. Let's say that x is equal to 1. If x is equal to 1, we get y is equal to 2 times 1 plus 3. Now, simplifying, we get y is equal to 2 plus 3, or in other words, y is equal to 5. And this is essentially how we solve for y just given x. And we can use this equation. Similarly, what the limit is trying to do is we're saying that as x approaches a specific quantity, then what is y? And we're usually given an equation to do this, and it's usually written in the y spot. Now this is essentially how we solve limits. Now when we're solving a limit, we just plug it directly into the equation. But in a general sense, the theory of limits, we are actually approaching that specific quantity. So when x is approaching this specific quantity, what is y? Or in other words, we're saying that x is equal to a specific quantity, what is y? So the two questions are very similar. In algebra, we're given the question, when x is equal to something, what is y? Now in limits, and especially in calculus, we're given the question, when x approaches some value, what is y? And that's essentially how we have a perfect relationship between algebra and limits. Okay. Now, let's actually start by solving a limit. So let's consider the first problem over here. We have the limit as x approaches 0 of 5x. And the limit as x approaches 0 of 5x is very simple to solve. Now, let's just first construct an equation. We're going to say that y is equal to 5x. Now, as x approaches 0, we want to know what is y. Now, when we're doing limit problems in calculus, what we usually just do is we just plug in the number. So we're going to plug in y is equal to 0, and therefore we get y equals 5 times 0, and we get y equals to 0. And that's essentially how we solve this limit. We're going to say that y is equal to 0, which means that the whole limit is equal to 0. Now, we can do this in a more algebraic sense with just plugging in values. Now, algebra can dealing with equations and a table, which we have x and y, which we've commonly seen in algebra. Let's just start by plugging in. Let's start by slowly decreasing. So we have 1. If we plug in 1 into 5x, we get y equals 5x, and we get y equals 5 times 1, and we get y equals 5. So if we keep doing this, we'll essentially see it approaches 0. Let's just organize it into a table. We organize it into a table. We'll see that we have x and y. When we plug in 1, we see that we get 5. When we plug in 1/10, we see that we get 5/10. When we plug in 1 over 100, we get 5 over 100. Now, if we plug in 1 over 1,000, we get 5 over 1,000. So as you can see, the values keep decreasing until, as this approaches 0, as x approaches 0, y is approaching 0 as well. And this is where we get the definition of a limit. As you can see, we're steadily decreasing the values, and this is eventually going to approach 0. Now this is going to be infinite, but as we can see, it's approaching 0. But what is y approaching? Y is approaching 0 as well, and that's the answer to the limit. Now what we've just done over here is we've done, let's just say this is 5x, y equals 5x. Let's just say this is going to be y equals 5x. Now notice that this is not the perfect line representation of y equals 5x because there's no specific coordinate system, but if we just say this is equal to y to 5x, we see that this is the origin, 0, 0. And if we draw a little bit bigger, we'll see that we have, so let's just do dot dot 0. We'll see we have this line intersect the origin. So as you can see, we have points located in this quadrant and this quadrant. Now, just for clarification, we're saying that this is approaching 0. It'll never reach 0. The reason we're writing 0 is here is we're just saying that it's approaching 0, hence the arrow marks. Now notice that there's never a physical time when we are approaching something that it equals to 0, but we're just writing 0 in this sense to say that it's approaching 0. Okay, so continuing. We have y equals 5x and it intersects at the origin. Let's consider the right-hand limit. So how do we do the right-hand limit? So consider the limit as x approaches 0 plus 5x. Now what does 0 plus mean? Well, we're saying as x approaches 0 from the right-hand side. So we're going like this. We can see the values originally are the greater, and then they keep getting smaller. And over here, as we've seen, this is essentially the right-hand limit. They approach from greater, and they approach to smaller. So this graph can be considered the right-hand limit graph. So this is essentially the right-hand limit. But what if we conduct the left-hand limit? In other words, what if we come from the left-hand side? So we see that this is equal to 0. What about the limit as x approaches 0 from the left? What is this equal to? Well, let's conduct and construct especially a graph. Now, well, this is actually a table, so let's construct this table. And let's essentially plug in values. Now, if we've seen from the right-hand limit, we start from a greater value, then get smaller. We're going to start from a smaller value, and then get greater. Now, obviously, we can't start anywhere on this side, because we're obviously just going to do the right-hand limit. Let's start from this side. Now, you might be thinking, well, if this is the x-axis and this is the y-axis, isn't this going to be negative? And indeed, it is going to be negative. So let's conduct -1 first. We plug in -1, we get -5. -1/10, what do we get? Well, we plug it in, we get -5/10. And now you also might be thinking, isn't -1/10 smaller than -1? Actually, it isn't. It's important to realize that when we consider greatness in mathematics, we're considering how far right to is it of some number, that we're considering our reference value. Now, right now, we usually don't have a reference value, but we can just pick our reference value to be -1. -1/10 is closer to 0 and farther and closer to the right-hand side. If we consider an arbitrary value to be a right-hand side, -1/10 is closer to that than -1, hence it's greater. Okay, so -1/10 is greater than -1. Let's say we have -1 over 100. If we do that, we'll get -5 over 100. -1 over 1,000, we get -5 over 1,000. And as you can see, it keeps going. Let's observe this. We can see that this keeps getting closer and closer to 0, as it just keep on going. Let's see this side. Now, as you can see over here, we have -5, -5/10, -5 100ths, -5 1,000ths. This is also getting closer and closer and closer to 0. So at the same time, this is getting closer to 0. This is also getting closer to 0. Now, just for clarification once again, when we're writing 0, we're actually saying that this never approaches 0 because we're saying it approaching. We're not saying it is getting to 0. But in this case, we're just writing 0 over here, just to signify that it's approaching 0, even though we're really never in the theory of limits actually getting to 0. So as you can see, this also equals to 0 in the left-hand limit. Now, when the right-hand limit, right hand, and the left-hand limit are equal to the same thing, we can say that that specific quantity is what the whole limit is equal to. But what happens if they disagree? If they disagree, then we write 3 letters, D, N, E. In other words, does not exist. If these vary, but they don't. So we can write 0. And that's how we essentially do the fundamentals of a limit. Now, every time we don't have to construct a table, plug it in, observe it on a graph, and so on and so forth. Usually we can just plug in 0. Yes, in the theory of limits we're approaching it, but we can just plug in whatever value x is approaching to. Okay, now that we've essentially learned the theory of limits, and then understood how to solve limits, understood what right hand and left hand limits are, let's continue to the second problem. So the second problem over here is a little bit more complicated than the first one. So we have the limit as x approaches 5 of 64 x squared minus 25 over x plus 25. So let's just plug it in. If we plug it in first, we're going to get x plug in into negative x plug. If we plug in 5, we're going to get 25 times 64 minus 25 all over. Well, we have 5, so we have to plug it in. So it's 5 plus 25. Simplifying, we get 25 times 64 minus 25 over 30. And still simplifying, we're going to get 64 times 25. 5 times 4 is 20. 6 times 5 is 30. That's 32. 0, 2 times 4 is 8. 2 times 6 is 12. We get 0. 2 plus 6 is 10. 3 plus 2 is 5. 1, 6. 1. So 1600. So we get 1600 minus 25, which is 1575 over 30. Now we're not going to try simplifying it, but we're just going to say this is the answer. Okay, so that's essentially how we just solve this limit. We just quickly plug it in, and that's all. Now let's consider a different problem. Let's consider the limit as x approaches 0 of x squared minus 49, or let's just pick a bigger number, let's say 81, all over x minus 9. Okay, now we're doing a specific problem for a purpose. Let's just plug this in. Well, let's say that x first is equal to 9. Now, if we plug in x is equal to 9, x approaches 9, and let's plug in x approaches 0 first. So let's just say we have x approaches 0. We're going to get 0 squared, that's minus 81, and 0 squared minus 81 is minus 81, and 0 minus 9 is minus 9, and we get 81 divided by 9, because these cancel, to get 9. So we obviously solved that, but let's try this. If we plug it in, we'll get 81 minus 81, which is 0, 81 minus 81, all over 9 minus 9, which is 0 over 0. And you might write this as your answer. You might write 0 over 0, or just write 0 as your answer. But this can actually not be your answer. This is an indeterminate form, and we do not write this in mathematics. In mathematics, when we have this specific type of format, we tend to not leave it like this, and actually you're not supposed to. But we can use a specific type of method. Now, what method are we going to be using? We're going to be using the canceling out method, but we need to know a little bit of algebra. Now, we need to know that the sum, or let's just say difference of squares, formula. Now, the difference of squares formula is known. We can't do the sum of squares, but if you consider subtraction as a form of addition, then you could say sum of squares. But difference of squares is what we usually call it. Now, the difference of squares formula can essentially be written in a sense that's way easy to comprehend when we're dealing with fractions in factoring. Now, let's just say we have x squared minus 81, or let's make it more general. We have a squared minus b squared. A squared minus b squared is equals to a plus b times a minus b. Now, this seems obvious when you use the binomial theorem, or just use this and distribute. We can use a times a is a squared, a times negative b is negative ab, b times a is positive ba, those cancel out, and b times negative b is negative b squared, and we get this. Now, this is very simple to do. Now, this is very important in factoring. As you can see over here, let's first split this up. So we have x squared minus 81. This is equal to x plus 9 times x minus 9. Okay, now that we've got this, let's write it on top. So we have limit as x approaches 9, and now we're going to write this, x plus 9 over, well, x plus 9 times x minus 9 all over x minus 9. Now, what is the reason that we're doing this? As you can see, we can cancel out these terms, and essentially, well, this is a part of a term, so this part of the term and this one term. And essentially, we'll get the limit as x approaches 9 of x plus 9. And solving, we get 9 plus 9 is 18. And that is the answer to the limit. Now, we don't use this when we just have x approaches 0, because we don't get an indeterminate form, or a form which we can't usually do or try to solve in limits. Now, that's why we do this, and that's a specific type of method, which appears a lot when we're dealing with limits. So let's recap what we did in this problem. Now, this problem was easy. We just plug in 5 and we got our answer. But the problem that we just dealt with right now is a little bit harder. It involves the difference of squares, and we have to use this difference of squares because it factors out the equation very well. And that's why the difference in squares is very special, because it essentially factors out the a squared and b squared effectively and can cancel out. So that's why the difference of squares is useful in limits. Now, we also use it in algebra when factoring, but it's also very useful in calculus as well. Now let's go to the hard part of the video. This is the derivative of 3x cubed. Now, we talked about how to do limits of basic algebra, then how to do limits of a little bit more complicated algebra, and now we're going to derivatives. Now, in order to essentially try to find what the derivative is, we can't use the derivative technique because we're presuming that we don't know anything about derivatives. We just know everything about limits, and we need to find what the derivative actually is. So we can just use derivative techniques to solve this really easily. But if we're actually considering that we're trying to find this using limits, we have to use a formula called the definition of the derivative. Okay. The definition of the derivative states that we have the limit as x approaches h, well, not x approaches h, as h approaches 0, of f of x plus h, subtracted by f of x, all over h. And this is essentially the definition of the derivative. So this is the definition of the derivative. The limit as h approaches 0 of f of x plus h subtracted by f of x all over h. Now this may seem complicated, but we have to understand that we can use this to essentially find the derivative of 3x cubed. Okay, so let's work this step by step. So we first have the limit as h approaches 0. This is one of the most important parts, because this is what we're going to be doing at the end. We're going to be substituting h is equal to 0. Now, let's consider this. We have f of x plus h, and then we have f of x, and we have h. These are also going to be very important when we're dealing with the problem. So let's begin by first essentially substituting 3x cubed into the limit. So we have the limit as h approaches 0, and the f of x plus h is going to be just 3 times x plus h cubed. And that's essentially going to be our major substitution, because then we can just do subtracted by 3x cubed all over h. And that's essentially what we need to solve the problem. So what this is going to end up in the end is we're going to be essentially spreading this out using algebra. And once we're done with that, this is just going to result in an algebra solution in which we just cancel out and divide, and we essentially get the answer. Okay, so let's erase this and let's begin. Okay, so we have the limit as h approaches 0 of 3x plus h cubed minus 3x cubed over h. Now let's expand x plus h cubed. X plus h cubed is just x plus h times x plus h times x plus h. So let's first multiply these two. This is just x squared plus 2x h plus h squared, and we're multiplying this times x plus h. So we get x cubed plus 2x squared h plus h squared x plus hx squared plus 2x h squared plus h cubed. Okay, so simplifying that, we get x cubed plus 2x squared h, and hx squared can be added to get 3x squared h, and we have hx squared h squared x specifically, and 2x h squared can be added to get 3x h squared, and then we just have h cubed, because we simplified that, and we just have that. So we have to have about 4 terms. So 1, 2, 3, 4, and we do have 4 terms specifically. Okay, so this is going to be the expansion for x plus h cubed, but it's important to realize that we have to multiply by 3. So we have to multiply by 3 for everything. So we'll just multiply by 3. We don't have to write it in parentheses. So we get 3x cubed plus 9x squared h plus 9x h squared plus 3h cubed. And this is essentially the expansion. Now we erase this. Our next step is to subtract 3x squared. So we subtract 3x cubed specifically, 3x cubed. These cancel, and we get 9x squared h plus 9x h squared plus 3h cubed. And we're going to divide this by h. Now the purpose over here, the reason we divide by h is so that it cancels out. As you can see, this cancels out. This cancels out 1. So we have 9x, and 1 of this becomes 1, and this becomes 2. So we get 9x plus 9xh plus 3h squared. And this is going to be 9x squared. Now, we have the limit as h approaches 0 of this, let's just erase this, of this expression. We plug in 0 for h, and we cancel these out, because 9x times 0 is just 0, and 3 times 0 squared is 0, and we get 9x squared remaining, and this is going to be our answer, 9x squared. Now you might be thinking, is this going to be the correct answer for the derivative of 3x cubed? Now, if we use the definition of the derivative, we get 9x squared. But if we use the techniques of the derivative, we get 9x squared. So therefore, using the techniques of derivative and the definition of the derivative, we've got the derivative of 3x cubed. And this is essentially how we find the derivative of 3x cubed, or just any specific type of function, using the definition of the derivative. Okay. Now that we've talked about that, let's recap. So in the beginning of the video, we talked about the limit as x approaches 0 of 5x. We talked about the definition of the limit, and we talked about the details and intricacies of the limit itself. And we talked about how the limit is essentially just trying to keep on doing multiple series of approximations till we get a specific point in which we know that it's definitely going to reach this specific number. Over here we have a little bit more advanced algebraic limit, and we solved that really quickly, and we considered another limit, which we had to use a special algebraic technique called the difference of squares. Over here, we essentially found the derivative of 3x cubed using the definition of the derivative, which is a limit as h approaches 0 of f of x plus h subtracted by f of x all over h. That's essentially the definition of the derivative, and we got 9x squared, which by using the techniques of the derivative is correct. It's important to realize that the techniques of solving for the derivative of a specific algebraic polynomial, which this is essentially is a monomial, and specifically to try to find it, they use the definition of the derivative. So as you can see, 3x squared, and we get 9x squared, 3x cubed, we get 9x squared for this. This is actually based on the definition of the derivative. So once you do multiple times of the definition of the derivative for multiple monomials, we essentially find a generalization. But this is how we do monomials, and we got the power rule in differentiation. Now that I've talked about that, we can make this video to an end. If you like this video, if you like this channel, please subscribe to learn more. Thank you.